It's now my pleasure to introduce Dr. Ricardo Betancur. Ricardo serves as an associate professor at the Marine Biology Research Division of Scripps Institution of Oceanography, UC San Diego, a position he has held since last year. His research interests lie in organismal marine biology with a major focus on phylogenetic inference and comparative analysis using fishes as study systems. This research approach prioritizes the implementation of genome-scale approaches for robust inferences in macroevolutionary research. Fieldwork is an important component of his research, and he has participated in multiple expeditions across 4 continents. Please join me in welcoming Ricardo to give his presentation.
All right, thanks, Rebecca, for the introduction, and to all other organizers of this wonderful symposium. It is a real honor to be here today and talk, share with Buck Fellows and mentors and others the research we do on fish macroevolution using phylogenetic approaches. So the history of life on Earth extends across a staggering 4 billion years. So in both terrestrial and aquatic realms, there have been numerous losers represented by the extinct groups and the winners that persist on Earth to this day. Now, the contemporary array of life comprises groups that underwent remarkable diversification, as well as ancient groups that, despite their age, contain only a few species today. So that is a common theme in macroevolution. So how can we study macroevolution or evolution over deep time? Since time scales in millions of years are not particularly amenable to experimental manipulation or direct study, we're left with 2 primary resources. And the first is, of course, the fossil record, which can reveal significant insights into changes in lineage diversity or morphology over time. However, more recently, the focus has increasingly shifted to the use of phylogenies. And with that background in mind, a major aspect of my research program deals with building phylogenies, much needed tools for robust macroevolutionary inferences. And this line of research centers almost entirely around the use of fishes as study systems. So here are some examples of previous studies addressing fish phylogenetics. The early ones are based on small multi-locus data sets, but more recently, through the NSF-funded Fish Life Initiative, a collaborative project that also includes the Smithsonian and George Washington University, we have been building trees using genome-wide exome data. And I should add that we initiated the development of the fish life markers during my tenure as a Buck Fellow here, so this opportunity played a significant role in this. Now, to address macroevolutionary questions with phylogenies, we use phylogenetic comparative methods, or PCMs. And combined with morphological and ecological data, PCMs can be used to study dynamics of diversification or to examine trait evolution over time and across habitats. So what type of macroevolutionary questions can be addressed with PCMs? My research is mostly centered around examining habitat transitions. So for example, I have been broadly interested in how transitions along the benthic pelagic axis in the water column have influenced macroevolutionary dynamics in multiple fish groups. And a classic example is the 3-spined stickleback in freshwater lakes of the northern hemisphere. So marine populations have colonized these freshwater lakes multiple times independently, and in most cases, lineages in those lakes tend to diverge into a limnetic form that is slender-bodied and feeds on plankton, and a benthic form that is deep-bodied and feeds on large bottom invertebrates. And this has happened not just once, but multiple times independently in different lakes, providing clear evidence that there are strong evolutionary forces driving divergence along this ecological axis. Other examples for this come from the popular cichlids in Central American lakes or the European whitefish. In all these lakes, again, sympatric lineages also reveal strong divergences along this vertical axis in the water column. Now, this all makes sense with very recent divergences, including sympatric populations of the same species or closely related species. But what about deep macroevolutionary scales? Do we see similar divergences along this axis in the water column over deep time? So we have been tackling this question from the viewpoint of several higher-level marine fish groups. And the first one here is what we call Carangaria. It includes flatfishes and other seemingly disparate taxa, such as marlins, dolphin fishes, jacks, barracudas, and archerfishes. But what is really relevant here is that Carangaria comprises lineages that lie at extremes along this benthic pelagic axis. So whereas marlins and dolphin fishes include some of the most remarkable open ocean pelagic swimmers, flatfishes are as benthic as they get. So the study here was led by my former PhD student, Emmanuel Ribeiro, who's now a postdoc at the University of Basel in Switzerland. And the goal was to assess how the KPG mass extinction affected the evolutionary dynamics in this group. And as we all know, the textbook example is that extinction of dinosaurs due to a KPG gave rise to irradiation of mammals during the Cenozoic. But what about the marine fishes? So the studies based on the fossil records, such as this one here by Matt Friedman, have shown an explosive diversification of spiny fin teleost in the aftermath of the end Cretaceous extinction. So here we have ancestral habitat reconstructions plotted onto the time tree of Carangaria, and we can see that major habitat shifts take place right after the KPG. So here is a habitat transitions right through time plot that makes it easy to see. We see this spike in habitat shifts right after the KPG, followed by a decline in rates later in the Cenozoic. The same pattern is observed for lineage diversification analysis. Carangaria is an evolutionary radiation, and we can see that the speciation rate is time heterogeneous, with all major lineages originating in an early burst after the KPG, followed by a rate slowdown. And finally, the same appears to be true for morphological disparity quantified using geometric morphometric analysis. So the plot here is a bit different than the previous two. Rather than looking at rates, what we have here is cumulative disparity over time. Regardless, the pattern is very similar. We see this steep increase in body plan disparity after the KPG. So in summary for Carangaria, all major lineages and body plans originated in an early burst shortly after the KPG mass extinction. An extinction of competitors ultimately allowed the occupation of newly released niches along the benthic pelagic ecological axis. All right, so next we have the snappers and the fusiliers in the family Luginidae. And this came out a few years ago, and the study was led by Melissa Rincon, a postdoc in the lab, and also Emmanuel. And a key question to ask here is whether evolutionary outcomes are predictable. And a landmark example comes from distantly related fast-swimming pelagic animals like sharks, dolphins, ichthyosaurs. As we all know, their body shape is highly streamlined, which is a convergent adaptation to the locomotion constraints imposed by the viscosity of water and drag flow. So our study integrates phylogenomic data using the fish-like markers that I mentioned earlier for over 80% of the species in the clade. And with this robust phylogenomic framework, we test three major predictions on evolutionary determinism using PCM. And the first is that transitions along the benthic pelagic axis occur multiple times independently within all major oceans. And to do this, we merge the results of ancestral habitat and ancestral range inferences onto the phylogeny. That way, we can estimate where and when these habitat transitions happen. So here, the star denotes benthic to water column transitions. And as we can see in these maps, there are stars in all 3 time slices and also across different geographies. So our results suggest that ancestral lineages live in benthic habitats and that independent and recurring invasions of the water column took place during different times and at least once within each of the major oceans, highlighting the ubiquity of habitat transitions in both space and time. Our second prediction is that there is a strong morphological convergence associated with habitat affiliation, particularly in water column lineages. And what we have here is a morphospace with the phylogeny or trait grams overlaying along the major PC axis. What we can see is that deep-bodied and slender-bodied fish plants lie at opposite extremes along this PC1 axis. And these largely correspond with bottom-dwelling lineages on the left and water column lineages on the right, although there is, of course, substantial overlap here in the middle. Along this PC1 axis, we also see major changes in the forking of the tail fin from a truncate tail fin on the left to a deeply forked tail fin on the right. Now, what is most remarkable here is that red branches that turn blue, which represent bottom to water column transitions, tend to cross from left to right along this PC1 axis. And that is a clear indication of convergent evolution linked to habitat affiliation. And on the left, we also have many statistics conducted to explicitly test for convergence in water column lineages, and they're all significant. So finally, our third prediction is that the water column lifestyle resulted in evolutionary dead ends, where the adoption of a new habitat regime can be advantageous in the short term, but in the long term can create an evolutionary trap due to elevated extinction, decreased speciation, or both. And the reason for this is that the more homogeneous water column should in principle provide fewer opportunities for diversification than benthic habitats, which are otherwise both ecologically and structurally much more complex, enabling microhabitat partitioning. Now, this third prediction hinges on 2 premises. First, we will expect that bottom lineages have overall higher rates of diversification than water column lineages. And second, that habitat transitions are either unidirectional or asymmetric. So in other words, we expect that shifts from benthic habitats to water column happen much more often than the reverse. And in line with the prediction, we do find that rates of lineage diversification are faster in bottom than in water column lineages, and also that habitat transitions are asymmetric, with bottom lineages transitioning much more frequently into the water column than vice versa, as we can see in this diagram with the arrows of varying thickness. Okay, so that's for snappers and fusiliers. But more recently, we have revisited this idea that transitions into water column may have resulted in evolutionary dead ends in 2 other marine clades, the surgeon fishes as well as the angler fishes and their relatives. What we see in surgeon fishes is that, first, there aren't any differences in diversification rates between bottom and water column lineages, and second, and perhaps more importantly, is that although transition rates exhibit asymmetry, they do so in the opposite direction of what we anticipated. As we can see here, there is a higher incidence of water column to benthic transitions than the reverse. So apparently, no evolutionary dead end here. The final example involves Lophiiformes, the angler fishes and relatives. And there is a single benthic to pelagic transition, apparently without any reversals. In this case, while there isn't much phylogenetic replication to examine the frequency of transition rates between habitats, at least we do see this expected unidirectionality. However, the sole transition into the bathypelagic zone by the ceratioids actually resulted in a massive evolutionary radiation, and this clade has super elevated diversification rates. Of course, this is a deep sea clade, and all previous clades we look at were mostly shallow, so not exactly comparable, but still, anglerfishes are clearly thriving here in the water column, so once again, not an evolutionary dead end. I tend to think this is probably more of an exception than a rule, but it still goes to show that macroevolutionary generalizations don't really hold up. In summary, for snappers and fusiliers, returning to the initial question of whether evolutionary outcomes are predictable, the answer is mostly so. Regardless of the geography or the age of the clade, whenever a bottom lineage transitions into a water column, its shape tends to change from a deep body plan with a truncate tail fin to a slender body shape with a forked tail fin. And these results ultimately reinforce the deterministic nature of evolution as a result of the similar use of niche space along the benthic pelagic axis. However, if we consider other clades, the question of whether transitions into the water column have led to evolutionary dead ends is clearly more nuanced. The prediction holds for snappers, but not so much for surgeonfishes or anglerfishes and their relatives. Okay, that's all I had. I'd like to thank all the members in the lab, our collaborators, Smithsonian, the Peter Buck Postdoctoral Fellowship Program, and NSF. Thanks for your time, and I'll be happy to answer any questions now.
Questions for Ricardo?
Hi, Ricardo. That was a great talk. I was curious. It seemed like there's a lot of variation in the dorsal and the adipose fin. Is there some expectation on how that would interact with the ecology, or is there something else that's causing that variation?
In the dorsal fin of what clade? The snap?
If you go to the one where you had the phylogeny, and then you had kind of the back.
This one?
No, one more, two more.
Oh, the
Yes.
morphospace.
The adipose fin and the dorsal fins really
Oh, yeah.
are different.
These are two outliers, really. These are really two outliers.
Are those ecologically driven, or is there something else driving variation?
I really don't know. I really don't know. But yeah, these are just two outliers with that crazy dorsal fin that's not very typical for snappers. Yeah. Okay.
Thank you, Ricardo, for a fantastic talk. And during his time, Lynn Parenti was one of his mentors, and the late and very missed Rich Vari was also one of Ricardo's mentors.